the University of British Columbia. And so he currently works on a variety of problems, including tools for scalable Bayesian inference, which is the basis of his talk today. But he's also done some really interesting work on Bayesian non-parametrics, streaming data, and Bayesian theory. Before he was an assistant professor, he was a postdoc in the Broderick group at MIT, and before that, he completed his PhD there under Jonathan Howe. So thank you for talking to us today, Trevor.
Thanks for having me and for the very kind introduction. Good, yeah. So today I will be talking about some very new work that has come out of my research group on large-scale Bayesian inference via data summarization. And we're calling this work Sparse Hamiltonian flows, and you'll see why a bit later. But I'm subtitling this Bayesian Coresets without all the fuss. So this is joint work with my two PhD students at UBC, Naitong and David. And the sort of algorithmic stuff that you'll see today was due to them. And then there's some theory that I guess dovetails with this work by Kian Naik and Judith Rousseau at Oxford. Okay, so large-scale data has become the norm in a very wide variety of scientific fields, from physics to biology. And as a statistician, I like to make inferences from data using probabilistic models. And those models, I mean, typically they come with some parameters. And what I mean by making inferences is that I try to understand what the values of those parameters are in the model that, in my model at least, dictate how the data were generated. And so when I process data, what I really want are good point estimates of those parameters in my model. But not only that, I want a good notion of uncertainty in those estimates. Whatever algorithm I use to process that data, I want it to apply to the sort of modern scale of data sets. So it has to be scalable. And so that it can sort of transfer to practitioners. I need the method to be easy to use. The big challenge is that, at least in Bayesian statistics, all of the methods that we have typically used were developed prior to this sort of deluge of data. And so they were designed with the goal of having good theoretical properties and quality guarantees, but not necessarily with the goal of being computationally scalable. And as it turns out, it's very difficult to get these two things together in one package: theoretical guarantees and scalability. And so that is kind of my big research challenge that fits into a lot of my work. I want to develop scalable, easy to use Bayesian inference algorithms with theoretical guarantees. And so I can sort of abstractify almost everything that I do into this really cute setup where I have some data, and let's call that X. And I want to infer some unknown parameter of interest, and we'll call that theta. In a little cartoon here, I'm just showing a two-dimensional example of this theta. So I've got theta 1 and theta 2 on the horizontal and vertical axis. And as a Bayesian statistician, I always start with a description of my knowledge of theta before observing any data. And we typically call that the prior distribution. And this, of course, allows us to incorporate any prior expertise or maybe lack thereof in a problem of interest. So here I'm showing you some contours in gray. These are probability density contours. So you can think of this distribution as being, let's say, an isotropic Gaussian or a standard normal distribution, where the mean is 0 and then there's some covariance. Okay, so again, as a Bayesian statistician, how do we include data in our analysis? There's this very nice I guess, principled way of doing it by treating this as a conditional distribution. So once I observe X, I condition on it. And what I'm left with afterwards is the posterior distribution, or the conditional distribution of theta given X. So throughout the talk, I'll denote that pi of theta, the density for that distribution. And the posterior gives us a wealth of options for coherent point estimation. So let's say the posterior mean, or maybe the density mode if it's unimodal, and uncertainty quantification. So let's say a posterior variance, maybe an entropy or something like that. And so again, you can see we've got contours here, and they're a little bit weird and warped because the posterior in general tends to take kind of a much more interesting shape than the prior. The main challenge in Bayesian inference is to estimate expectations under the posterior distribution. So if you give me some function f that you're interested in, the goal here is to estimate the conditional expectation of f of theta given x. And of course, we can write that as an integral of f under the distribution pi. Now, I can estimate this expectation to sort of whatever degree of accuracy I want by taking samples from pi. And so I can relabel this problem as sampling from the posterior distribution. So in this talk, we're going to cover methods for doing this with large-scale data. The, I guess, remaining to be the most common way of doing Bayesian inference today is Markov chain Monte Carlo. And the idea of Markov chain Monte Carlo is that we run a Markov chain for which the stationary distribution is actually that target posterior distribution. And so what you might do in practice is you'll start your Markov chain, you'll pick a value of theta somewhere way out here, and you'll run your Markov chain. You'll take these sequential steps one by one. And if you've designed your Markov chain right, it will slowly make its way towards the main mass of the posterior. And once it reaches that mass, it'll kind of bounce around in there sort of seemingly randomly. Now, acknowledging that I started the Markov chain from just somewhere I picked, I want to throw away these few samples that don't represent the posterior well. And so typically in practice, what you'll do is get rid of the first, let's say 20% or 30% of your states in that Markov chain. And then for the remainder, I'll just forget the ordering. Instead of treating these as a sequence of states, I'll just ignore the fact that it was generated from a Markov chain. And what you're left with is a collection of states, unordered, that looks a heck of a lot like a sample from the posterior. Now, although this seems kind of magical, I mean, it seems like, I'm sweeping a lot under the rug here. Actually, this methodology is quite easy to use. It's widely applicable. Designing this Markov chain is not too hard. I mean, there are very advanced methods one can use where it is a little bit trickier to figure it out, but the basic Metropolis-Hastings algorithm that, would be maybe the first thing you would try in almost any problem, it is quite easy. You can write it down in just a few lines of pseudocode. Markov chain Monte Carlo is sort of founded on 30 years of very rigorous theoretical results that all sort of tell you that if you run this Markov chain for long enough, then this sample set will eventually look or enable you to compute posterior expectations with increasing accuracy. So in some sense, it's exact in the limit of large computation. The problem with MCMC is that it's just not tractable for large scale data. The easy way to see this is that if I'm designing my Markov chain to know about this posterior distribution, I essentially have to make sure that I'm evaluating that posterior density or something proportional to it in every single step. And if I'm doing that, then I really have to look at every single one of my data points in every single step. And so, of course, when I have a lot of data, this can be quite slow. You might think, well, let's just subsample the data in every step then. And as it turns out, there's some really nice theory coming out recently, one paper from James Jondro and collaborators that basically argues that this cannot work. There are reasons why this fails. In this work, we're going to take a slightly different approach. I am going to look for and build a small weighted subset of data. I'll call that a Coreset. And you'll see that we're going to call the density of this Coreset pi w, where this w here indicates some weights in my subsample. And I'll use this as a proxy for posterior inference instead. And the hope is that I can build a pi w that's close to pi, and then I don't have to worry about pi anymore. And I can just focus on this much cheaper weighted subset of data posterior. Now, you might reasonably ask, why should I even bother with this idea? And as it turns out, when you have large data, most often it exhibits a significant degree of redundancy. So even in these three little examples, classification, clustering, and regression taken from a textbook, there's not a really spectacular amount of data here, maybe 1,000 points or something like this. But even in this case, you can see there's a significant degree of redundancy. Right? Let's just take the regression problem as an example. If I wanted to model this with a line, and so my parameters are the intercept and the slope, I really don't need to keep around all of this data to have a good understanding of what those values are. Right? I could probably throw away most of this data and still capture that information. And so this is a phenomenon we see across a wide variety of problems. As long as your model is not too complicated, do you expect your data to be essentially, there's a large amount of redundancy in it. And so the goal of this talk then is to find such a Coreset. Now, as it turns out, this is made very difficult by the fact that I cannot easily sample from this approximation pi w. And worse, I can't compute the normalization constant of it. And that depends on w now, right? It's no longer a constant. If I'm trying to tune w, I need to worry about the normalization constant for that density. And I can't compute it in general. So this is quite challenging. In this work, the way that we deal with this is to use the key insight that you just shouldn't try to directly sample from this Coreset posterior, and you shouldn't try to directly compute or estimate its density. What you do instead is you build what's called a variational flow that targets the Coreset posterior. What I mean by a variational flow, we'll get into a little bit later, is basically if I start from a very simple distribution, let's say a Gaussian, and I pass it through some function, and it's parametrized by, let's say, some parameters lambda, then I can create a family of functions such that it has the flexibility at the output to match the Coreset posterior. And so now I have these tunable parameters w, and maybe I have some tunable parameters in this function, but because I'm treating this as just a simple distribution mapped through a function, I can use a transformation of variables formula, and I can get densities, and I can take IID samples very easily. And this just turns the problem of Coreset construction into an optimization problem. I can just try to find values for these parameters lambda and w that makes the distribution at the end of this mapping as close as possible to pi. So this function, because it targets the Coreset, it's efficient because it's only looking, when I evaluate this function, implicitly my data get in there somewhere, but I'm only using the Coreset, so this is efficient. Unlike the standard Coresets approaches, because now I'm working with this just mapping of a function, from samples from a Gaussian, map it through a function, I can very easily obtain IID samples. And by transformation of variables, I can evaluate the density. And the beauty of this is that this is very simple to train. Past Coreset methods have been quite complicated. With this one, you just minimize the KL divergence between the output of the flow and the target. Along the way, we'll see some theory on quality. And I should mention very briefly that there's some concurrent work by Martin Jankowiak and Du Fan called Surrogate Likelihoods for Variational Annealed Importance Sampling, where they also sort of realized this idea of connecting a flow to a Coreset. They don't call it a Coreset, they call this a surrogate likelihood, but it's mathematically kind of equivalent. Okay, so let's dig in, and we'll start with a little bit of notation setup here. I'll give you some background on Bayesian Coresets. So the models that I'm studying in this talk are those that have conditionally independent data x given my parameter theta. And so I'll denote my log likelihood function for just one data point, log p xn given theta. I'll denote that script ln of theta. Of course, being Bayesian, I'm worried about my latent parameter, and so I can treat my data point here as kind of just a fixed value. My prior density, I'll denote pi naught of theta. And my goal is to sample from the posterior distribution with density, as I mentioned before, pi of theta. This is proportional to, using Bayes' rule, the likelihood times the prior. And so I have pi naught of theta, that's my prior, and I have the exponential of the sum of all my log likelihood functions, and that's the likelihood. Now you can see that if I wanted to evaluate pi of theta or something proportional to it, I would have to loop over all of my data. And when n is large, this can be very expensive. So in this context, a Coreset is a sparse weighted sum of log likelihood functions. So instead of looking at this whole sum of all of my log likelihood functions for all of my data, I'll multiply each of the functions with a weight. These weights will be non-negative, and most of them will be 0. So if only a small number of these are non-zero, then actually evaluating this Coreset log likelihood will be much cheaper than the full log likelihood function. let's assume that I can find a nice setting of these W's. Then what I can do is in my Bayes rule, I can just replace my exact log likelihood function with this Coreset log likelihood approximation. And now I have a Coreset posterior density pi sub W that is much cheaper to evaluate up to normalization, as long as these weights are sparse. And so as I mentioned before, in a lot of problems, there is redundancy in your data that you can take advantage of. And we find this in a lot of examples in practice. So starting with just some acute synthetic example, in a paper a few years ago, I looked at a very toy logistic regression problem in 2 dimensions. I've got some blue points and some red points that I want to classify. And the true sort of classification plane between them that I use to generate the data is just a vertical line. In this case, you can summarize this data set of about 10,000 points down to about 10 points. And so you've gained, a factor of 1,000 in computation time for each log likelihood evaluation. The black points here, by the way, denote Coreset points. You can kind of see that this model is being very nicely summarized by one point that is kind of orthogonal to the plane of interest. Here's another synthetic example, but it's quite pathological, actually. This is a Gaussian location model. It's 100-dimensional, and there's no correlation between any of the variables. And so this model is really, it's just, you're just trying to fit noise, essentially. Here we can reduce our data set down, as you might suspect, to about the dimension of the space. So we can reduce our data set down to about 100 points. And I guess the original data set here was 10,000 points. But I don't think the original data set size matters so much in these problems. It's more the sort of fundamental dimension of the model itself that matters. And in this case, this is about 100 dimensions. One slightly more realistic example that I've worked on is a basis regression for housing prices in the UK. And here, this is a 300-dimensional problem. And you can kind of see this. What I'm showing here is the mean regression plane of housing price. And you can kind of see the shape of the UK here. And we've managed to compress this data set, which I think is 1 million data points or close to, down to about 300. Now, this is wonderful, right? But the problem is if it takes more work to find this thing tractably, then there's kind of no point in doing it. And not only that, if there's no quality guarantees that you can get with a method to find this Coreset, then you can't really trust it, right? What's to say that there's a good approximation out there? So how do we actually build this thing? In the early work on Coresets, so this is a paper by Jonathan Huggins and myself back in 2016, the idea was to subsample the data set with non-uniform weights or non-uniform probabilities. And you subsample it down to some very small size, and then you reweight the points in the subsample with a set of importance weights. As it turns out, this kind of method is sort of fundamentally not, it just doesn't work. The reason for this, let's just take a little toy logistic regression example, blue points, red points. I need to find a plane that sort of splits these 2 classes. The reason is that when you generate a Coreset by subsampling, you don't really get a good representation of your original data set. So in this cute little toy example, let's take a Coreset of size 3 as an example. So here we go. I've subsampled 3 points. I've got 2 red points and a blue point. If I then run posterior inference on a model based on just these 3 data points, I'll get a classification plane that looks something like this. It splits the 2 red points and the blue point. But if I did this whole exercise again, I just randomly picked a Coreset of size 3, I might get 3 totally different points. And again, I run posterior inference, and I'll have this green plane that separates them. And I'll do it again, I'll get another green plane. And what you may be noticing is that none of these planes that I'm learning from these Coresets look anything like the decision plane that I would want to learn if I actually had access to all of the data. So just subsampling and reweighting is maybe not a great idea. In recent work, there has, well, I guess, following up on that, I decided, well, okay, picking points by subsampling is not such a great idea. It's too noisy. And so let's try to be more intelligent. Let's try to sort of pick one point at a time. So these methods indeed involved somehow intelligently selecting a data point to add to your Coreset, and then running some optimization to re-optimize the weights, and then iterating this procedure until you build up a Coreset of the size that you want. Now, as it turns out, this method constructs very good Coresets in general, assuming you can tune it well, which that's, there's a lot of asterisks on that. But let's assume you can tune the method well. What this method typically does is it starts by, well, the first data point you add is usually not going to be a fantastic representation of your posterior. In this logistic regression model, you probably want at least 2 data points to summarize the decision plane in 2D anyway. And so my first data point that I'll add will just be somewhere. It doesn't really matter. There's not much it can do. But now that it has one red point, it has the opportunity to improve the Coreset significantly by just adding a single blue point. And then this procedure iterates. It keeps adding one point at a time, sort of intelligently. And very quickly, you can see that you can get convergence to a very good posterior approximation using a very small amount of data. So this sounds really great in theory. In practice, this re-optimization step is very slow. The way that we found that is sort of the right way to formulate this is as the minimization of the Kullback-Leibler divergence from the Coreset posterior pi w to the true posterior pi. And for those who may not be familiar, the Kullback-Leibler divergence is the expectation under, in this case, pi w, our Coreset posterior, of the log density ratio of pi w and pi. So you can see where some problems might come up here. First of all, I don't know the normalization constant on pi w. So I can't actually evaluate this density. And remember, the normalization constant depends on w now. So it's not just a constant. So in this paper that I've written a few years ago, we used some clever algebra to get around this problem. Maybe not the most satisfying solution, but it does sort of address the issue. The bigger problem is that I cannot sample tractably from this Coreset. And if I want to estimate or get an unbiased estimate of this KL divergence, I have to sample from pi w. In our paper, we use Markov chain Monte Carlo for this. But of course, now I have this kind of crazy algorithm, right? It's an inner loop, outer loop method where the inner loop is taking MCMC samples to run stochastic gradient descent. Woof. I don't know if you've tuned any one of these things by itself before, which is already a significant amount of work. Trying to do it all together is very, very challenging. In theory, this method is it's tractable because you're only ever working with the Coreset, but in practice, it's really tough to tune. And it's slow to run because of this inner and outer loop method. So this method is kind of a proof of concept of the existence. This is what we use to often show that there exists a good Coreset, but it's not fast enough to be practical to actually speed up if you were to use this speed up posterior inference. Okay, so we've got these kind of 2 big problems that we need to solve. The first is that this one at a time, sequential greedy, iterative, picking a point and then optimizing, it's just too slow. It's actually kind of hard to implement and certainly hard to tune. And number 2, and this is maybe the harder of the 2 problems, I can't sample from pi w. So even if somehow I'm able to make this outer inner loop method fast, I still need to be able to sample from the Coreset to train w. Sort of alongside this problem is another one, which is that I don't know the normalization constant. Okay, let's deal with this first problem because it's a bit easier to handle, and we'll deal with the second one a bit later. So it turns out it's the return of subsampling. That one at a time optimization is slow. It's hard to implement, it's hard to tune. The insight in this work, one of the big ones, is that you can pick the data in the Coreset by subsampling. Wait, hold on, didn't I just tell you that subsampling is not good? Right, we did this whole little doodle with noisy Coresets. The point is that you pick the data in the Coreset by subsampling. You don't pick the weights with an importance weighting procedure. You leave the weights as parameters that you can optimize. So here's an example. I mean, the intuition behind this is that if I pick enough points to put in my Coreset, there exists a good weighting that I can find. It may be difficult to find it, but there exists a good weighting, and then I can sort of kick that can down the road and say, okay, let's suspend your disbelief for a little bit longer, and we'll get to the method to tune the weights later. Okay, so let's go back to our little cartoon logistic regression problem here. Let's take a sample, a Coreset of size 3, again, just as a little example. And as I showed you before, this is of course no good, right? I've got my 2 randomly selected blue points and 1 randomly selected red point, and my Coreset posterior mean here is really no good. But if I increase the weight on this blue point, and I increase the weight on this red point, and I decrease the weight on this blue point, lo and behold, as it turns out, you can get a good posterior approximation out of this. I have not told you yet how to change these weights in this way, but there exists a weighting that makes this work, right? Let's take another example. Here's a totally crazy example. I've got 2 blue points and a red point again, and my decision plane is almost orthogonal to the one that I originally was looking for. But if I increase the weight on this blue point and increase the weight on this red point and decrease the weight on the blue point, once again, I can force this subsampled set of data to have weights that make it a good Coreset. This intuition comes with some theory. So this is where some of the asymptotic work that Kian and Judith did. The key result is that after this subsampling procedure, the optimally weighted Coreset, I haven't told you how to get it yet, but the optimally weighted Coreset is an exact or near exact approximation of the posterior. The key assumption is that the space of log likelihood functions that I'm working with is close to finite dimensional, right? So you can think in like an exponential family model, a conjugate exponential family, it is finite dimensional. Truly, there are just some sufficient statistics that you work with. In our theory, we assume that it's nearly finite dimensional, so it doesn't have to be finite, but it's close to some, there's a subspace of dimension D that kind of very well approximates all of your log likelihood functions. We require that the remainder, whatever's left once I project into finite dimensions, the remainder is sort of well-behaved, uniformly smooth. The tails are, they don't vary too quickly, that kind of thing. And we also have some assumption about the concentration of the posterior. I don't think we need this assumption. It's sufficient. I don't think it's necessary for the analysis. I do think this sort of near finite dimensionality is necessary, just because I'm compressing. I'm compressing my data. I have to assert that there is some underlying sort of simple version of the model. So here's the result. If my Coreset size is at least the dimension of this underlying log likelihood function space times log n, where my Coreset size is m and my data set size is n, then the optimal weighting for my subsampled Coreset, the KL divergence for that Coreset posterior to the true posterior converges to 0 with probability that converges to 1 as the data set grows. Some remarks about this. This is not sort of a pathological convergence. This is something like 1 over square root n in models that you would run into in practice. Again, yeah, this probability convergence is something like, if I remember correctly, 1 minus 1 over n, right? So again, not pathological. This result actually improves if the log likelihood functions are indeed truly finite dimensional. Then the result is actually that the optimal KL is actually equal to 0 with high probability. So there is a perfect compression of your model if your model is truly finite dimensional. Right, so this is good. I mean, this is very comforting, right? This says that if I just start by subsampling, I haven't really lost anything. So instead of doing this inner and outer loop fancy sort of intelligent selection thing, we're going to start by picking m data points to chuck into our Coreset. That's quite easy. That's maybe one of the fastest algorithms I routinely use on a daily basis. And it is supported by theory, right? We have not limited ourselves much by doing this. We still need to figure out how to tune those weights, but at least we haven't lost anything yet. All right, let's move on to this much more challenging problem of sampling from the Coreset posterior and dealing with the fact that we don't know the normalization constant of the Coreset. As I mentioned before, the key idea is that you don't try to sample directly from that Coreset posterior. You're not going to do something like MCMC on it. What you'll do instead is try to construct a variational family that lets you get close to that Coreset posterior and then draw samples from that instead. So how does this work? Well, first of all, I need to have you take one little leap of faith. We need to actually add some auxiliary variables to our Coreset posterior. They're going to help us construct these maps. And so I have my latent variable theta that I'm originally concerned with. I'm going to augment that with what I'll call a momentum variable, rho. These are sampled independently. The theta variable that we've looked at before is coming from the Coreset posterior, and the momentum variable is coming independently from some reference distribution. I'll call it R, but you can in your head think of it always as a standard normal distribution. How does this method work? Well, what we'll do is we'll start by sampling a value, let's call them theta naught and rho naught, from some simple distribution Q naught. And again, anytime I mention a simple distribution, it's always going to be a standard normal in our code and in practice. So you can just replace this Q naught with IID from normals. Then we'll map the sample theta naught and rho naught through a function T sub W. And this thing has to be invertible. It has to be differentiable. The inverse has to be differentiable, right? So this is a diffeomorphism. And once I've mapped these two values through this function TW, I'm left with theta and rho at the output. And I can use the sort of standard transformation of variables formula to write the density of the output. And this, of course, now depends on W because the mapping depended on W. So this output density, I'll call that QW. This procedure, I haven't told you anything about this map TW yet, but this procedure is quite nice a priori, right? I can generate IID samples very easily by just generating theta naught and rho naught from this standard normal and then passing them through this function. I can evaluate the density, including the normalization constant of QW for any value of W by just using the sort of standard transformation of variables. And because of that, because I have IID sampling and I have densities, I can actually tune the weights and other parameters if there's other parameters in this map, but I can tune them using variational inference. If any of you are familiar with this, this is, as you've seen before, minimizing over some parameter the KL divergence of our approximation to the target. Now, in this case, the target is the posterior, right? This is the true posterior pi. And because I'm working with a sort of augmented space, I have to augment the posterior. I'll just augment that with the same reference distribution as we had before. So you'll notice, nowhere yet I have the Coreset posterior in here, right? I've got Q naught, it maps through TW, we get to QW, and then I minimize the KL from QW to pi times R. Where's the Coreset? This is where the Coreset comes in. My goal, my challenge now, is to pick this mapping TW such that for any value of W, this output QW is something like pi W times R. If I can do that, if I can find a map TW such that that's true, then if you plug in pi W times R into this KL formula, what you're actually doing is minimizing the KL of pi W to pi, right? And remember how tough that was before. Well, now it's no longer difficult because we have the density, we have IID samples, we don't have to worry about it. So this is not trivial, right? Designing this map TW to accomplish this, certainly not trivial. And I actually don't think we've sort of fully solved this problem yet, but the sort of first stab that we have in this paper is as follows. We're going to construct what we call a sparse Hamiltonian flow. And now, yeah, in this case, this reference distribution that I mentioned, this is going to be a standard normal for this slide. So the idea here is that we need to interleave a couple different kinds of mappings that achieve different goals in order to make sure that if I run this function TW, that it gets me really close to pi W. So this is called Coreset Hamiltonian dynamics. If anyone in the audience is familiar with Hamiltonian Monte Carlo, you will see some analogs here. And this new idea called quasi-refreshment. So I'll just describe the algorithm. I'll describe the algorithm for computing this map TW. First, I sample theta naught rho naught from my reference distribution Q naught. So again, something like a standard normal. And then I'm going to run a loop for big case steps. Oh, and by the way, I'm drawing a little doodle down here. This is the Coreset, the Coreset posterior contours pi w. And here I've drawn some theta values, these red dots, and some momentum values, these arrows, from my standard distribution. Okay, the first thing we're going to do is propagate a dynamical system, starting from each of these theta and rho pairs. We're going to initialize at theta, in this case, on the first iteration, it'll be theta naught rho naught, but we'll initialize at theta k rho k. And then we'll simulate Hamiltonian dynamics. So the velocity of the theta position is rho. That's why we call it a momentum. And the acceleration, i.e. the change in rho over time, is the gradient of the log Coreset density. This is the secret sauce. If there's one slide in the talk that you should pay attention to, it's this one right now. The beauty of this is that this dynamical system I can simulate by only looking at the data in the Coreset, right? Because I have the gradient of the log of the Coreset density. Of course, the normalization constant here goes away. I don't have to worry about it because I have the gradient of the log. And this only depends on the Coreset data. And so I can simulate this dynamical system very efficiently. Okay, so let's see what happens to this, this set of contours here. I start with my reference, and then what happens with this Hamiltonian dynamics is that the density kind of slides. If you think of the contours of this Coreset posterior, it kind of slides down the contours, right? It prefers, well, I mean, I guess climbs up maybe is a better way to describe it, but it prefers regions of high Coreset posterior mass or high Coreset posterior density. Now you can see what's happened here. All of my momentum variables now are pointing very strongly to the right? Because I'm now sort of sliding towards the Coreset posterior, I'm moving all of that mass to the right. And so this momentum distribution is no longer anything like a standard Gaussian, right? So in some sense, in order to keep improving this approximation of pi w times r, I really need to somehow reset the momentum variables so that they look again like a standard normal. So that's where the quasi-refreshment comes into play. The idea is that you just take the momentum variable that comes from your Hamiltonian dynamics and you shift it and you scale it by some value. Intuitively, this is what you use to sort of re-standardize the momentum. You set the mean to 0 and the standard deviation to 1. Of course, right now in this situation, the mean is like, 500 and the standard deviation is something. It doesn't really matter. The shift and the scale parameters become parameters that are optimized during variational inference. So remember how we said on the previous slide, if you have this map, you can just formulate this whole thing as a variational inference problem. Well, these are just parameters that show up in that inference. Okay, so let's look at this contour again and see what happens when I standardize the momentum. It resets it to something like this. And then I just iterate. I loop this procedure. So I'll run Hamiltonian dynamics again for a step, and then I'll re-standardize the momentum, and then I'll run Hamiltonian dynamics again. And slowly but surely, you can see that this is sort of pushing the mass into all the nooks and crannies in the Coreset posterior. And if I run this loop for long enough, if k is large enough, I kind of hope that this will eventually work its way towards pi w times r. And so that's the map, that's TW. If I apply TW enough, I should kind of hope that the output of the sequence of maps, the distribution looks like pi w times r. And so then I can compute the density of this thing now. I can compute, I can take IID samples, and so I can now optimize the weights W and any refreshment parameters here, the shift and the scale. What does this look like in practice? Well, if I print for you iteration number sort of going along the flow, we use the leapfrog algorithm to simulate those dynamics. And so this is showing the sort of leapfrog step number. On the y-axis, I have the elbow, the expectation lower bound. Higher elbow means that there's a better posterior approximation in my flow. And so you can see every 10 steps, we do one of these shift and scale, these quasi-refreshments. And so this is kind of an interesting figure. What it shows you is that when you're running the Hamiltonian dynamics part of that iteration, it doesn't really change the KL. It doesn't improve the approximation. All it's doing is it's sort of interchanging momentum and position, the sort of energy of these two states. What does improve the quality of the flow is the quasi-refreshment steps. Basically, you run the Hamiltonian dynamics, it improves the values of theta, but it sort of twists up the distribution of rho. And so then you use the quasi-refreshment to bring the distribution of rho back to something that looks reasonable. And then, of course, you use Hamiltonian dynamics again to sort of, transfer the potential energy into kinetic energy, and then you just repeat. And so it is the quasi-refreshment that's sort of gaining us quality, but it only works because we've run the Hamiltonian dynamics in between. Okay, so that is the second problem. Instead of trying to sample from the Coreset posterior pi w, we create a function essentially that takes a reference distribution and pushes it as close as it can towards pi w. And then we use the transformation of variables formula to get densities. We can easily generate IID samples. And we use these two properties to formulate a big variational inference problem that we can solve. Okay, this is a cool idea. Does it work? Does this actually, is this fast in practice? Is this easy to tune? Is it simple to implement? We studied 3 models in this work, a couple of synthetic ones. I always like to do a Gaussian location model because I know everything about it. I can evaluate KL divergences in closed form. I know normalization constants of everything. You can make the problem pathological by increasing the dimension. And so it's sort of a very nice test bed. And of course, if your method doesn't work in a Gaussian location model, it's really not going to work on anything. So it's a nice sort of starting test. So we have a latent variable theta. That's the mean of the likelihood Gaussian. The covariance is 100 times the identity matrix. I have 10,000 data and my dimension is 10. Moving to a slightly more realistic model, I have a logistic regression with a heavy-tailed prior. So my latent variable is generated from a Cauchy distribution. And then my observations are Bernoulli variables 0 or 1 that depend on some features, xn. This is a data set of commercial flights that we studied. It had 15,000 data points, 10 dimensions. The features that we were using for training the logistic regression were weather conditions, departure time, arrival time, things like that. And the response variable here was whether the flight was canceled. We also studied a linear regression model, slightly non-standard, so that is not totally conjugate. We have our slope variables beta and our noise variance log sigma squared that are coming from a standard normal. And then as usual, we generate the response variables as a linear function of the features, and then we have some variance. We studied the same commercial flights data set, and in this case, the response was the departure delay in minutes. We did a couple comparisons. I'll start with the Coreset comparison. We compared to uniform subsampling, one of these fancy sequential greedy methods that I mentioned earlier. This is Hilbert OMP from an earlier paper of mine, but you could sort of mix and match other ones here. We, in green will be our sparse Hamiltonian flows algorithm. Sparse VI, this was this sort of sequential greedy method that I mentioned. This one was just too slow to run on these 15,000 size data sets. So we weren't able to test against that. All right. Let's see, we have 3 figures for our 3 experiments: Gaussian location model, logistic regression, linear regression. Moving to the left on the x-axis here is more compression. So this is a smaller Coreset, lower computational cost for inference. And on the y-axis, I'm showing you the KL divergence. So lower is a better posterior approximation. And as you can see, except for this very simple Gaussian location model, where we actually cheated for this Hilbert OMP method, we essentially gave it the posterior distribution to help it match the posterior distribution, which is sort of back circular. Aside from this example, the sparse Hamiltonian flows across essentially every Coreset size, it's sort of unquestionably the best method to use. It's the easiest to tune. It's just a single stochastic gradient descent. So you tune the step size on your optimization, but that's it. And in this case, the Gaussian location model, I guess, was 10-dimensional. So once you get to a large enough Coreset size, for the Hilbert OMP method, it gets somewhat easy to approximate in this very simple synthetic model. In these real models, it really struggles, and so does uniform subsampling. So for my money, this is the way to go. Of course, there are constraints for the sparse Hamiltonian flows. You have to have real space variables because you need log gradients, let's say, of the Coreset posterior density. But for now, anyway, I think this is the right path forward for Coreset construction. We also compared to other flow methods, right? So we use the Hamiltonian flow to construct an approximation to our Coreset. Other people have developed other kinds of flows also based on Hamiltonian dynamics previously. So we've got a couple here. We've got Hamiltonian importance sampling and unadjusted Hamiltonian annealing, just two flow methods that also use Hamiltonian dynamics. There's some weird caveats about these algorithms because it's not tractable when you have a large amount of data to train these because the flows are very expensive to run. What they do is they actually subsample in the flow while it's running. But of course, that ruins the ability to compute the density because your flow it's a mixture of flows at that point, right? It's sort of like every single step in your flow, you're subsampling. And so you get this really crazy mixture of flows. So it's not actually tractable to compute the density. So in order to give us a method that was sort of possible to compare to our ability to compute densities, we built a Hamiltonian importance sampling and unadjusted Hamiltonian annealing on a uniformly subsampled Coreset as sort of a standard baseline. And then, of course, we looked at our sparse Hamiltonian flows algorithm. Once again, on the y-axis, I'm showing you for our three problems, the KL divergence, lower is better. And on the x-axis, I'm showing you the number of optimization iterations to train these flows. So moving to the left is sort of easier to train, fewer iterations. And you can see across the board, now these plots ignore computation time, right? So the dark purple and the dark blue are the full, very expensive flows to train. And despite the fact that we're giving these methods the full data, you can see that they struggle quite a bit more than the sparse Hamiltonian flows to match the posterior approximation. The light blue and pink, these sort of test methods that sort of have valid density estimates, they did not perform well at all. So once again, the punchline here is that building a flow that targets a parametrized Coreset and then optimizing those Coreset weights in the variational inference training step is, I think, the right way to build a Coreset. And it's a particularly nice way to build a variational flow too. Okay, I'm not going to show you all the detailed timing results, but the punchline here is that, as you might expect, we're quite a bit faster than other methods. Specifically, we're about 2 orders of magnitude faster than NUTS. So the trade-off actually occurs at about 100 samples. If you want more than 100 samples, it's worth it to run our training procedure and then take samples from our flow versus just sampling from the beginning with something like NUTS. Okay. That is, I guess, the sum of it. So in this work, we introduced a new flexible, tractable, you can think of it as a variational family for large-scale data. You can think of it as a way to construct Coresets. We provide some theoretical guarantees on quality. I think there's still some work to be done there, but this is a very exciting start. And I think this has opened the door to a lot of new work on data summarization. Yeah, but there is a lot of work left, designing better refreshment schemes, applying to discrete variable models, looking at better optimization routines for training, and then, of course, the list goes on. The paper QR code is there on the link if you're interested, and I think that is it for me. Thank you very much.
Oh, thank you. That was great, Trevor. Cool. So is there any questions from the audience? See, Filippo actually had a question, but I think...
Yeah, I typed one in the chat.
Cool, you want to just ask it then, Filippo? Sure.
Yeah, when you're iterating to find the map, oh God, it was a few slides ago. There was a map called T of K, T of H, something like that. I was wondering what the criterion it is what criterion you're using to decide when you stop iterating because the map is ready.
Very good question. Very good question. Yes. So in this paper so far, we just have this as a user specified parameter. We have not yet worried about deciding how long to run the flow for, but this is absolutely something that one should consider, right? Because if you run the flow longer, sort of conceivably, you're getting a better approximation of your Coreset posterior at the end of the flow. And so then when you minimize the KL divergence to the true posterior, you're actually getting sort of a better approximation. On the other hand, it's more expensive the longer your flow is. So yeah, we absolutely have not answered that question yet. In all of our experiments, I think we did 10 iterations of Hamiltonian dynamics and refreshment. And then I forget how many leapfrog steps we did for the Hamiltonian simulation. It was on the order of 10 or 20, something like this.
But if I understand correctly, you're comparing two distributions, right? What you start with, and do you use the KL divergence there to sort of see how different they are, or do you just evaluate them at certain points, or?
Yeah. So you're evaluating it at the end of the flow, so after that K iteration, but you actually could use the KL divergence to get a notion of when this flow has sort of converged in a sense. Right?
Yeah, or the Wasserstein distance, or that sort of things I was thinking.
Yeah, exactly. In fact, I had that slide up earlier that shows you sort of what happens to the KL divergence as you run the flow, right? The Hamiltonian kind of didn't do much, but then you do the quasi-refreshment and it jumps. So you can actually monitor this, right? You can just see like, hey, my steps aren't buying me anything anymore. Let me just cut off the flow here.
Yeah, that's what I was thinking, yeah.
Yep, you could totally do that.
And also I was thinking when you showed the plots, it was interesting to see that not all curves were monotonically decreasing.
No. Yeah, these flows are, well, they can do some very weird things. They can, so there's the caveat with so let's see, is there an example of one here? Yes, okay, so at the beginning, you can see that these flows kind of get worse and then get better. The one caveat that I kind of swept under the rug is that this is the marginal KL divergence. So what we're doing here in these models is we're essentially, we're projecting away the momentum variable, and then we're just looking at, in fact, just looking at an estimate of the KL divergence for the marginal distribution for the latent variable theta, which is what we care about, right? These algorithms are all optimizing the joint KL with the momentum variable. And so sometimes it might decide, oh, I want to make the momentum distribution much closer. I'll sacrifice a bit of the position variable to do that. And so that's why you might see that these curves actually go up at times.
Very interesting. It makes sense. Thank you.
Yeah, great questions. Thank you.
Thanks.
Cool. Well, actually, if there's no other questions from the audience, I'm going to be selfish.
I had my hand up if you didn't mind, Stephen.
No, go ahead, Andrew.
I'm going to butt in on you and be rude. Thank you very much for the talk. I have a few questions that I suspect are my own misunderstandings and less to do with other things. On slide 9, you point out your two big problems to do with computing that KL. And I definitely agree those are the two key problems. Is the third problem not the fact that you still have pi of theta in there? Like you still have an expression for the KL that's the full posterior.
Man, you guys are catching all the things that I've swept under the rug. Yes. So in the KL divergence, the pi does appear, but it appears in a particularly gentle way. I don't think I want to flip through a billion slides to get there. That would be sort of visual disaster. But basically that pi, it has a normalization constant, but you can get rid of that because it sort of pops out of the KL optimization. It's a constant, doesn't depend on the parameters at all. So that goes away. The remainder is a sum of log likelihood functions. Now, as you say, this is an expensive sum to compute. In practice, you don't ever compute that sum. You do stochastic approximation of it. So let's say when you're training, for every gradient step you take a subsample of those data points from the full data set. Now, I told you at the beginning that subsampling doesn't work. That was specific to MCMC. For stochastic gradient descent, it's actually well known that subsampling, or I guess in general, unbiased stochastic estimates of gradients actually work perfectly well. And in the large scale data regime, it's actually very wise to only compute stochastic gradient estimates instead of the full gradient.
Yeah, cool. Yeah, I was just concerned that you'd swept the big N problem from one place to another. But and then I have two kind of picky questions.
Sure.
One is that sometimes I care about tail behavior of posteriors quite a lot.
Yep.
Like my functional is a tail probability or some function that heavily influenced by the tail behavior.
Yes.
And Coresets, I would expect, are mostly focused on the bulk of the distribution. So I wonder how, like, is there any way to give the Coreset some knowledge of my functional to like make it emphasize its contribution to the expected integral or something like that?
So to me, this is one of the most compelling features of Coresets compared to other approximation methods. The Coreset will obey the tail behavior. So imagine I have, a heavy-tailed prior, and this is kind of a canonical example, a heavy-tailed prior, and then I have whatever likelihood, doesn't really matter. But the data are only in sort of some subspace. And so you have unidentifiability in the orthogonal subspace, let's say.
Yeah.
The Coreset posterior will also be unidentifiable in that orthogonal subspace, and the tails will still be heavy-tailed, right? It's sort of, because you're using the data and the probability model that you originally started with to form your approximation, you respect things like unidentifiability, like tail behavior, like weak identifiability. And so to me, this is very compelling. The one caveat now is that with the flows, they may not respect, at least not after finitely many of these Hamiltonian flow and quasi-refreshment iterations. And so you do have to run enough of those iterations so that your flow is actually sort of percolating out into the tails and understanding that behavior.
Yeah, cool. Often I see like lots of these approximation algorithms make assumptions that very much constrain how heavy their tails can be. So that's very nice.
The previous Coreset construction methods, especially this, this Hilbert OMP method that I have up right now, that absolutely focuses on the bulk of the mass. Implicitly, it'll get the tail behavior, I think, generally reasonably, because again, you're still basing your approximation on the data and the model that you started with. But it may struggle a little bit more to capture the right tail behavior.
Very nice. And then my final picky point is that T of K is a diffeomorphism. And I wonder if that's ever restrictive. So there's
very restrictive.
Yeah,
very
restrictive. You can do a lot of stuff with diffeomorphisms, but like posteriors can get even weirder. I know there was a presentation we had a few weeks ago on continually indexed flows, which relax this kind of assumption a little bit. And I wonder if you had investigated or thought about any ways to kind of get around diffeomorphism or bijectivity.
I have heard of these works. I have not looked into them in any great depth myself, but I suspect that, the sort of core essence of this work is nothing to do with Hamiltonian anything, nothing to do with diffeomorphisms. It's really the notion of making some, I guess, starting with a simple distribution, mapping it through some function that depends on your Coreset weights, where the output looks like your Coreset posterior, right? So whatever function you want to put in between that does that, whether it's one of these continually indexed maps or something else, it really doesn't matter to me. I think the framework that we've come up with here is flexible to that. And I agree with you. I think you could probably do a lot better for the actual design of the function.
Nice, cool. Well, thank you again. Great talk.
Yeah, thanks for your questions.
Cool. Well, I think we've hit the hour. And that was really enjoyable, Trevor. Thank you for that. That was really interesting. I am going to just ask one very quick question. So nearly finite dimensional.
Go on.
So like one thing I'm very interested in, which ties into some of your older work, is unsupervised clustering, right? And we like to infer the number of components present.
Yep.
And so we could use something that's infinite, like the recently processed prior or something, or sorry, mixture of mixtures or whatever. Or we could use something like an overfitted mixture, which is strictly finite, right? But how would a Coreset work in that? Because I would imagine that if you construct a Coreset, the clustering is, I just don't see how you can have like over concentration of your components. And
So
issues generally.
Yeah, so there's a couple of tricks here. One is that if you are truly in sort of a non-parametric or a Bayesian non-parametric setting where as you get more data, you actually expect to uncover more and more clusters.
Yeah.
I mean, that's tough to compress, right? Because the more data you get, your model is sort of growing. Now,
Yes.
if you had let's say a Dirichlet process mixture and it was well specified, then you're introducing new clusters very slowly, right? Log n, something like that. Then your data is still compressible because after, however many data points, you're introducing clusters slowly and each cluster has a lot of data in it. So then you're going to get redundancy within each cluster. And I mean, again, I think there exists a Coreset in this case. Okay. Mixture models have other problems with like, you usually have to use discrete variables and things like that. And so that automatically disqualifies this particular function that I've come up with here, at least. As far as the fundamental compressibility of it and like whether there even exists a good Coreset, I think it really just comes down to how quickly are those new clusters introduced. If it's something like a heavy-tailed model, you're never going to compress your data much more than like, a power, right? Because you're just getting new information constantly. But yeah. In fact, we've had some experiments on mixture models in the past, and indeed you can still compress these things. Now, admittedly, these were not particularly complicated mixtures. I think it was a fixed K in those cases. But there's nothing fundamentally wrong about having a flexible value for the number of clusters. It's just how quickly do you introduce new clusters? That's the big problem.
Cool, thank you. And one other question, which I don't think applies to this, but I remember Dan Feldman once commenting on his Coreset work that by actually constructing the Coreset, you kind of smooth the likelihood and can help with overfitting problems. Have you? I don't think that will apply here, but I'm curious if you have any intuition on this.
So I believe, I think his intuition is more that subsampling, in a sense, robustifies, right? And in my case, I have found, so I admittedly have not done a lot of work on the frequentist side of not like optimization and computational geometry side of Coresets. In the world of Bayes, subsampling does not work by itself. Like it does, and indeed it will make you robust, like it'll sort of automatically reject outliers, right? Because they're just low probability. So if you're subsampling, you'll lose them. But your posterior approximations are generally no good with subsampling. Yeah, in fact, that first paper by Jonathan Huggins and we did all this work. I mean, the math in that is just so challenging. And we did all this work and we finally got the algorithm put together and we ran it and it was maybe a tiny improvement on just uniform subsampling. And the theory is beautiful. We were just really unimpressed with the performance. And that kind of kicked me down this path of like, okay, what's going on here? I'm very convinced by the philosophy of this approach, but just the mechanics of it, I can't figure out. And then there went optimization and things like that. So yeah, the just subsampling, I think does robustify you, but in Bayes, it's just.
Yeah. Cool. Well, thank you for that. I suppose we'll let you go to breakfast probably.
Back to sleep.
Yeah. Thank you very much. And thank you everyone for joining us.
Thanks, folks.
Bye-bye.
Thanks again.
Have a good rest of your day.
Thank you.